So we're gonna cover this one section in the electrochemistry chapter because it's in our course outline. This is balancing redox reactions. So we've talked about redox reactions, and we learned what redox, oxidation, and reduction are. So here's a brief review because maybe you've forgotten. We had the mnemonic oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. We talked about oxidation states. And we said that oxidation was an increase in the oxidation state. In this example, we have calcium going from an oxidation state of 0 to an oxidation state of +2. An increase in oxidation state, it is being oxidized. And we have hydrogen going from +1 to 0, a reduction in oxidation state. When we balance equations, chemical equations, the masses have to balance, meaning if I have one calcium atom here, I have to have one calcium atom there. But the charge must also balance. It's possible to mass balance a redox reaction, but not balance the charge. And so that would be incorrect. So the way we do this is we take the equation and we break it into two half reactions. We're going to look at the oxidation and we're going to look at the reduction separately, balance them individually, and then add them back together. So that's the overview. So we're also going to review oxidation states. So I know this didn't make sense to a lot of you at the first time around, so maybe it'll make more sense now. So we follow these rules in order of priority. Free elements have oxidation states of 0. Monatomic ions have an oxidation state equal to their charge. Okay. So oxidation state and charge of an ion are related and sometimes the same, but oxidation state is not the same as charge. So we just have to be a little careful there. The sum of oxidation states of all the atoms in a compound is 0. Basically, if you have a polyatomic something, all the oxidation states in there have to add up to whatever the charge is on the something. If it's a molecule, they all add up to 0 because the molecule doesn't have a charge. So neutral molecule, 0. A polyatomic ion, a group of atoms together with a charge, all the oxidation states have to add up to the charge on the ion. So nitrate ion has a charge of -1. So the oxidation states of the nitrogens and the 3 oxygens within it have to add up to equal the charge. In their compounds, metals always have positive oxidation states. Group 1 and group 2 metals have the oxidation state that is equal to their charge. The nonmetals is the one we have to really think about. And we follow this order of priority. And this is where I talked about noodles. Pho. Right? It's spelled wrong, but it was close enough. It should be PHO. Pho. Noodles. So fluorine, hydrogen, oxygen. The nonmetals would like to have, this is me personifying them, they would like to have the charge that they take as a monatomic ion. We learned how to do that. The halogens like to be -1, oxygen likes to be -2, etc. And so this gives us an order of who gets their way. So fluorine gets to be -1. Hydrogen gets to be +1 after we've allowed fluorine to be -1. Next in priority is oxygen, and then we go group 7, group 6, group 5. There's reasons behind this, but we're just going to learn the rule. Pho 765. Okay, so now that we reviewed that, here's the procedure for balancing aqueous redox reactions. Some of these occur in acidic solution and some occur in basic solution. And the process is similar, but there's just a little extra step for basic. So we'll talk about acidic solutions first. First of all, you have to assign oxidation states to all the atoms, and you have to figure out, okay, what's being oxidized and what's being reduced. You have to do that so that you can separate the overall reaction into two half reactions. You'll look at the oxidation and the reduction as two different equations. And then you balance each of them with respect to mass first. So balance everything other than hydrogen and oxygen. We save the hydrogen and oxygen to mess around with because this is in water. And water contains hydrogen ions and hydroxide ions in very small quantities and lots of water molecules. And so we can play around with those. Balance everything but hydrogen and oxygen, balance oxygen by adding water where needed, and then balance the hydrogen by adding hydrogen ions. This is an acidic solution. There's going to be hydrogen ions. After we've balanced by mass, we balance by charge. So look at the charges. The charges are not going to be equal on each side of the arrow. And so we're going to balance those by adding electrons. Then what we need to do, we've got two balanced half reactions. We need the number of electrons in each reaction to be the same. So if one of them has 3 and the other has 2, we need to do some multiplying so that we get them equal. Then you add them together. Because you made the number of electrons equal, the electrons will cancel out, and then double check it. So that maybe didn't make a whole lot of sense. We're going to do some examples. So for reference, here are the instructions on the side. We're going to balance this redox reaction. Okay? So we have to assign oxidation states. What's the oxidation state of solid aluminum? 0. How about this copper 2+ ion? It's 2+, +2. And here we've got aluminum, so that's going to be +3, and copper is 0. Elements are 0 by themselves. Monatomic ions, oxidation state is the same as the charge. We have to identify what's being oxidized, what's being reduced. So aluminum going from 0 to +3, oxidation or reduction? Oxidation. And then the copper is the reduction. Okay, so I'm going to write those separately. Your book always writes one on, I forget which one on top and one on the bottom. It doesn't really matter. I'm just going to go with aluminum for the top one. So I'm going to have aluminum solid going to aluminum 3+ aqueous. So that's one of them. And then the other one is copper 2+ going to copper solid. So I took the aluminums because they were involved in oxidation, and I made them into one half reaction. And I took the copper ion and copper atom and made that into another one. I keep the Cu2+ on the left side and the Cu on the right side. You don't switch sides. That would mess things up badly. Now I need to balance with respect to mass. Is this mass balanced? It is. 1 aluminum, 1 aluminum. The fact that it's lost 3 electrons, does that really matter? No, and we're going to take care of the electrons later. We're just looking at atoms, okay? So this is mass balanced. How about this one? Also mass balanced. Cool. Okay, so then we jump to number 4. Balance with respect to charge. Well, I have a +3 charge on this side and 0 charge on that side. I need them to be the same. I don't care what they are, they just have to be the same. But all I can do to mess around with it is add in electrons. Electrons have negative charges. So if I put electrons over here, I can reduce this charge, right? But I'm going to need 3 electrons. 3 electrons with their negative charge will add to the 3+ and give me overall 0 on this side, and then I have 0 on that side. So what do I need to do with the copper one? I need 2 electrons on the other side. You'll always end up with electrons on opposite sides because this one has lost electrons and this one is gaining electrons. One's oxidation, one's reduction. If I add these 2 equations together right now, 3 electrons here and 2 electrons there are not going to cancel out. That wouldn't work because when this process happens, 3 electrons are released. When this process happens, 2 electrons are taken. But what happens to the other electron? It can't just be out there by itself. So I need to find the least common multiple for 2 and 3, which is 6. So I'm going to multiply this one by 3, and I'm going to multiply this whole equation by 6. I'm sorry, 2. So I'm going to just put it in here now. So that would be 3 here and 3 here. Yes, 2, sorry. Because 1 times 2 is 2, not 3. 2 and 2, and this would be 6. Well, let's get rid of this guy. And then doing the same down here, you can see I really just didn't leave enough space. This would be 6, and this would have a 3 in there, and this would have a 3 in there. When I add these together, I've got 6 electrons on this side and 6 electrons on that side. Because 2 aluminums are going to become 2 aluminum ions, releasing 6 electrons. The 6 electrons are going to be taken by 3 copper ions to make 3 copper atoms. And so the electrons don't actually show up in the balanced chemical equation. I end up with 2 aluminums plus 3 copper ions. To make 2 aluminum ions plus 3 copper atoms. Any questions? Then you should double check. Yes?
Are names of the activities used for this for the ACS?
No, we're not using activity series.
So you're not writing the electrons?
Pardon me?
You're not bringing down
We're not writing the electrons in the balanced chemical equation because they don't actually appear as a reactant or a product. They get transferred from one to the other, but they're never actually just floating around by themselves. Yeah.
You could count them as the ion charge.
You could. In this one, you wouldn't have to go through all the steps. You could mess around with this one to get the charges on each side to balance. But there's a lot of equations that's not going to work. And there are some chemical equations that if you don't recognize them as a redox and take them apart and put them back together, you're going to spend hours going in circles trying to balance them. It's just like super hard to balance. Let's do another one.
Unless you get lucky.
Unless you get lucky. Yeah, that doesn't often happen though. Okay, so oxidation states, hydrogen ion, what's its oxidation state? +1. And chromium? 0. H2? 0. And chromium 2+? +2. Okay, so far these have been pretty easy oxidation states. So the hydrogen ion and the hydrogen molecules go together, and these guys go together. So I'm going to try to think ahead a little bit better this time. So I've got H plus AQ, and I've got H2 gas. And then I've got Cr solid and Cr2+ aqueous. First I balance by mass. So for this one, and these are still simple equations, so I have 1 hydrogen here and 2 there, so that tells me I need to put a 2 over here, balance the hydrogens. And then I'm going to go balance the other one. What did I do here? I'm becoming an alchemist, and I'm turning chromium into copper. That's not right. That'd be tough to balance. Yeah, that would be awesome. Okay, so that one's already mass balanced. So now we balance the charges. So here I've got 2 positive charges. So that means I want to put 2 electrons over here, because on the other side there's no charge. So we're going 0 on each side. And then here I've got chromium, 0 charge, and a +2 charge over there. So I need to add 2 electrons here to balance the charge on that one. Okay, so now we need to make the number of electrons equal, but cool, they're already equal, right? So then we add them together. The electrons, we think of them as canceling out. They get generated and used, and so we don't need to think about them. So I should probably just keep the same order that was given earlier. 2H plus aqueous plus chromium solid, and that's giving us H2 gas plus Cr2 plus. Any questions? Let's see, how many do I have these? Which one do you want to do? Copper and nitrate or iron and permanganate? Okay, we'll do this one. And then tomorrow I'll do the other one. Okay, so now the steps are missing on the side, but I think we can do it. So first thing is what? Assign oxidation states. So the iron is +2. Let's skip that one for now. The iron 3 plus, +3, and manganese is +2. Now we have to deal with the permanganate. This is a polyatomic ion. So all the oxidation numbers in here have to add up to -1. We've got nonmetals in here. We've got manganese. But manganese isn't a group 1A, group 2A metal. It's going to have a positive oxidation number, and that's about all we can say. So oxygen in that list of nonmetals, well, it's the only nonmetal here, so it gets what it wants. What does it want? -2. Okay, so the oxygens are -2, and there's 4 of them. They're each -2. And so here we have manganese. We don't know what it is. We'll call it X. And that has to add up to the overall charge on the ion. So this is X plus 8 equals -1. Yes, thank you. Those pesky negatives. So then X equals 7. Right? So here manganese is +7. And that may seem like a really high number to you, but that's what it is. Some of them do that. So now we've got our oxidation numbers, oxidation states. Well, we've got oxygen here, and there's no oxygen on the other side. Let's not worry about it, though, because this is an aqueous solution, and we can figure that out. Let's make sure we can find an oxidation and a reduction reaction among these other guys. Well, here's iron going from +2 to +3, so that's oxidation. And we've got manganese going from +7 to +2, reduction. So I'm going to take the iron, Fe2 plus, and on the other side, the only term that has iron in it is the Fe3 plus. And then I've got the permanganate ion and the manganese. So I'm going to put those in the other equation. Whoops. Okay?
We don't have to worry about it, like, this is a net ionic, or a net equation?
No, we're not really worrying about net ionic or anything like that.
The oxygen goes away, not worried about.
The oxygen is going to get taken care of. It will. So this, we're going to balance by mass. This one's already balanced by mass. This one is not. Okay, we hadn't come to an example like this before. The manganeses are fine, manganeses. But there's oxygen here and there's no oxygen there. So we balance oxygen by adding water molecules as appropriate. Well, we've got 4 oxygens here, so then I need to add 4 water molecules on the right side so that I can account for the oxygen. That make sense? Now I created a different problem, didn't I? I introduced hydrogen. This is acidic solution, and so we're going to balance the hydrogen using hydrogen ions. So over here, I've got 4 times 2. I've got 8 hydrogens. So over here, I'm going to put 8 hydrogen ions. And that's how I achieve mass balance. It may seem like we're throwing extra things in. Does it seem like that? This is in acidic aqueous solution. In an aqueous solution, you've got as many water molecules as you want. In an acidic solution, you have plenty of hydrogen ions. So it's just that we're identifying that some of the solution is participating in the reaction. It's not that we're throwing in things that weren't actually there.
YH plus.
YH plus, because it's acidic solution. In an acidic solution, we have extra hydrogen ions. That's what makes it acidic.
What do you do is H?
Well, we wouldn't have H negative. Hydride ion does exist, but it would not be found in an aqueous solution.
If you did H3O, you'd be in a lot more trouble balancing it.
Yeah, you could balance it using hydronium ion, but it's going to make things more challenging. You can do it, but you can see why we often just pretend that the hydronium ion is just a hydrogen ion. It just makes things simpler. And so we tell ourselves, yeah, we know that's not what it really is, but just this is easier. So we've got mass balance, we need to balance charge. We've got +2 and +3. So that tells me I need 1 electron on the right side. So I get +2 on both sides, right? We're not going for 0 necessarily, we're just going for equal. And then down here, now we've got a bunch more charges we have to be careful. So here there's 8 positives and a negative. So we've got a total of +7 on that side, right? And over here, I've got a total of +2. So how many electrons do I need to add to the +7 to get it down to 2? 5. So 5 electrons over there. Now the charges balance. Now what do I need to do? Yeah, we need to get the numbers of electrons the same. Here I have 1 electron, here I have 5. So I need to multiply the top equation by 5. So I'm going to put a 5 here, and I'm going to put a 5 here, and I'm going to put a 5 there. I chose 5 because I want 5 electrons to match up with the 5 electrons over there. And then I take these two equations and I add them together. So the 5 electrons and the 5 electrons are always going to go away because we set it up that way. And then I'm just going to copy down what's left. Now, the order in which you copy it down doesn't really matter. I often just use the same order that was given originally.
You have to include the hydrogen.
You do have to include the hydrogen. Yep. So for the iron, Fe, 2+, there's 5 of those. And next was permanganate, and there's only 1 of those. And then I can't leave out the 8 H pluses. So that's all the reactants. And then over on the product side, I've got 5 iron ions, Fe3+, and I have 1 manganese ion, and I have 4 water molecules. Okay? Do you remember the permanganate titration we did? The purple stuff. How could we forget that, right? That equation had, I think it was like 12 hydrogen ions in it. And we added sulfuric acid to the titration flask, right? And some people forgot to add the acid. And so they added the permanganate to the oxalate, and they swirled, and nothing happened. It was hot. They did everything else, and it didn't react. Because the hydrogen ions are participating in the reaction. They are involved in the reaction. And so we can't just ignore them. They are in there. They're participating. Any questions? Okay, so what if it's a basic solution? We've got one additional step. Everything else is the same. So you identify the oxidation states, you separate into 2 half reactions, you balance each half reaction by mass, balance everything but hydrogen and oxygen, balance the oxygen by adding water, balance the hydrogen by adding H+. It's all the same. Last extra step. Instead of an acidic solution where we have hydrogen ions, this is a basic solution where we have hydroxide ions. And so what we're going to do is we're going to add enough hydroxide ions to the equation that has hydrogen ions in it to neutralize them. And just add the same number of hydroxide ions to each side. So we need to do an example of this. Let's do this one because we already did a permanganate example, and this will just be slightly different. I think that's the last one. Yeah, so just this one last example. So, oxidation states. Here we have hypochlorite ion, 2 nonmetals. Chloride would like to be -1. Oxygen wants to be -2. Who gets their way? Oxygen. Ph. Fluorine, hydrogen, oxygen, 765. Oxygen wins. Oxygen gets to be -2. What does chlorine have to be? +1. These two have to add up to the overall charge. And here we have, there's an ion we haven't seen before, right? Well, we're just going to follow the rules. Here we've got hydrogen and oxygen as hydroxide. And then overall, this has a -1 charge. So you can approach this looking at that as hydroxide. You can also look at it as just hydrogen and oxygen and the FHO. Hydrogen gets to be what it wants. It's going to be +1. Oxygen gets to be what it wants because we still have the chromine to take up the slack. So together, these guys are -1. There's 4 of them. You following that? So that's total of -4 from the hydroxide, the OHs. And then we've got the chromium, we'll call him X, and this has to add up to -1, right? Because the overall charge on this whole thing is -1. So what's X? +3. So the chromium is +3. We go over here. Might as well do the easy one first. Chloride, what's that one? -1. Here we've got CrO4, 2-. Kind of, yeah, chromate. Well, oxygen gets to be what it wants, -2. So here we've got 4 oxygens, so that's a total of -8, right? And this has to add up to -2. So X must be 6. So the chromium is +6 there. So this one has chlorine in it, and that one has chlorine in it. So these guys are related. What's happening to the chlorine? Oxidized or reduced? It's being reduced. It's going from +1 to -1. So it's getting lower. And the chromium's going from +3 to +6. So that's being oxidized. So I've got hypochlorite going to chloride. And then I've got this complex ion here. Yes?
Will there ever be a case where there's different ones getting oxidized and reduced, like multiple ones?
That could happen, but we won't do that to you.
Okay.
Yeah. Yeah, you could have like 2 things being oxidized and 3 things being reduced and all kinds of crazy things happening, but we're not gonna pull one of those on you. First, balance by mass. Okay, so here the chlorines are fine, but the oxygens are not. And so I need to add water to the right side to balance the oxygens. That creates a problem with hydrogen. So I have to add how many hydrogen ions to the left side? 2. So I've got 2 hydrogens. and 2 hydrogens, 1 oxygen, 1 oxygen, 1 chlorine, 1 chlorine. What's the extra step? The hydroxides, right? Just, yeah, so we're gonna take care of the hydroxides before we go into balancing the electrons. So on this side, I ended up with 2 hydrogen ions. So I'm going to add 2 hydroxide ions to both sides. Is it still balanced? Yeah. So there's the mass balance for that one. And then the bottom one, here's chromium and chromium, 1 of each, 4 oxygens, 4 oxygens, 4 hydrogens. So I need to add 4 hydrogens over here. Now it's mass balanced for acidic solution, but this is in basic solution. So I add hydroxide ions equal to the number of hydrogen ions I have. 4 OH minus. And then I need 4 of them on the other side. And it got off center there. So mass balance is fine, right? Then we need to take care of electrons. There's lots of charges here, aren't there? We could simplify this a little bit before we mess with the electrons, or we could just plunge ahead. What do you want to do? Plunge ahead? Okay, we'll go with that. So what's the total charge on the reactant side? We've got -2, +2, and -1. So overall, -1. And what's the total charge over here? -3. We've got 2 hydroxides and the chloride. So I need 2 electrons on the left. And then the bottom one, here I've got a minus charge and 4 minus charges, so that's -5 on this side. And over here, well, these guys, 4 pluses and 4 minuses are canceling themselves out, right? Those add up to 0 and -2. So I've got -5 and -2. So I need, how many electrons over here? I need 3. Okay.
Multiply the top one by 3, the bottom one by 2.
Yeah, we have to multiply the top one by 3 and the bottom one by 2. And this is getting messy, huh? Maybe we should do a little simplifying. If I put 2 OH minuses and 2 H pluses together, what do I get? 2 waters. So what I'm going to do is I'm just going to rewrite that, because that's just going to be so much easier to look at. So that's 2H2O liquid. And then over here, 4 hydrogen ions and 4 hydroxide ions. That'll make 4 water molecules. So I'm just going to write it that way. That's a little easier to look at. Okay, so we could do more simplifying, but I think that's okay for now. So we need to multiply the top one by 3 to get the same number of electrons on each side. So that's going to be 6 and 6 and 3 and 3 and 3 and 6. Here I need to get 6 electrons also, so I'm going to multiply everything by 2. So this becomes 8 and 2 and 2 and 8 and 6. Everybody okay? It's a lot of little pieces to keep track of. But as one of my kids said, it's not rocket surgery. It takes a minute, doesn't it? Okay. I'm going to throw in yet another color. We have to add these together. I'm going to look at this and see if I can cancel some things out. The electrons are going to cancel out. So 6 electrons there and 6 electrons there. Same on each side, so we don't have to worry about that. We've got some other things that can cancel out too, right? I have 6 waters over here, and I have 3 waters and 8 waters. Well, so the 6 here, I could take any combination I wanted over there. So I'm going to cross this out. I'm going to get rid of 6 on that side, and I'm going to get rid of 6 on this side. So I'm going to say, well, there's just 2 of them now. Okay with that? And we can do something similar with the hydroxides too. Here's 6 hydroxides and 8 hydroxides. So these are all going to get used up, and there's going to be 2 left here. So I'm going to cancel that one out, and this is going to be just 2. So just did a little simplifying before I add everything together. So I'm going to copy things down now. 3 hypochlorite ions and 2 CrOH4 minus aqueous. And then I've also got the 2 hydroxide ions left. And then on the right side, I've got 2 chromate ions and 3 chloride ions and 3 plus 2. Look, I've got 3 waters here and 2 there. So that's 5. 5 H2O. If you didn't cancel things out here and just copied everything down, that would be fine, but then you need to simplify when you get to the bottom. And you should always double check, because would it be easy to make one little mistake and get the answer wrong? Oh yeah, really easy. Any questions? So now in theory, we know how to balance redox equations in acidic and basic aqueous solutions.